Good. And what's the derivative of cos? Negative sine of x. Beautiful. Okay, very good. So now what we're going to do is we want to figure out what's the derivative of tan. And we're going to develop it ourselves. Okay, what's the derivative of tan? Now, recall these identities. Tan of x is equal to sine of x over cos of x. And secant x is equal to 1 over cos of x. You guys remember that? There's cosecant, that's 1 over sine of x. There's cotangent, that's 1 over tan of x. This is secant, it's 1 over cos of x. Okay? All right, so we're going to find the derivative of y equals tan of x. Well, tan of x, we know, is equal to sine of x over cos x. So now we're going to take the derivative, and we're going to use the quotient rule. So the quotient rule says the bottom times the derivative of the top. And we just said the derivative of sine of x is cos of x minus the top times the derivative of the bottom. And the derivative of cos of x is negative sine of x. So what I'm left with here is cos squared of x. Oh, what do we forget? All over. All over.
Miss, is Nigel here?
Oh, Nigel. Okay, I'm going to have to fix it in a minute, okay? Just give me a second. Okay, so what we're left with here is cos squared of x plus sine squared of x all over cos squared of x. What can I do from here?
The numerator equals 1.
It does. The numerator equals 1. That's our Pythagorean identity. 1 over cos squared x. But what's 1 over cos of x?
Secant squared.
It is. So 1 over cos squared x is going to be 1 over cos squared x will be secant squared x. And that's the derivative of tan. Have you guys ever seen this before? You know what that means? Has anyone ever seen that? It's in Latin, it means end of proof. When you end a proof, that's one way that you can end a proof. Okay, so now you know. What about Joseph? Is Joseph off? So yeah, so that's one way to end a proof, too easy. Another way that you can see in math textbooks, a little FYI, is a little box, little black box like this, little square. That's another way. Or you can see double stripe, right? These are all ways to show end of proof. Good. All right. So the derivative of tan is secant squared x. And of course, now we have to use the chain rule if our argument is not just x, right? I mean, x is easy when you take the derivative, it's just 1. You don't have to show it. But if I have something like 5x, then I have to take the derivative of that 5x. Okay? That's all that we're showing here, just like always. Okay, so let's do these examples. So differentiate tan of 2x plus 5x squared. So derivative of tan is?
Secant
Good. Just secant?
squared.
Good. So secant squared of your argument. And our argument is not just x, so we take the derivative, and we see that the derivative is 2 plus 10x. Now, from what we learned yesterday, can I leave it like this?
No, we have to bring it to the front.
You got it. Thank you. And that's the way you should go. the higher degree? No, these are not polynomials. No. Okay, let's try this one. So now I have y equals cos of x minus tan of x, all raised to the third power. So, who wants to try? Somebody wants to try. I know somebody does.
3 cos of x minus tan of x all squared times negative sine x minus secant squared x.
Beautiful. Excellent. So it's our chain rule. 3 comes down, whatever is inside, right? Your function here stays the same. 3 minus 1 is 2, and then you take the derivative of the inside. Now take a look at that second bracket. What should I do there? I've got negative sine of x minus secant squared x. What should I do? Yes.
Factor out negative 1.
Yes. Do I have to move anything around here?
Put the secant squared x first.
It doesn't, not really. It doesn't matter. You're not going to leave marks. You can leave it like this. But what I meant was, you see in the first example how we took this, we took this and we brought it to the front? You don't have to do that here. And the reason is, these are just expressions. It's not my angle. It's not my argument, right? Whereas here, I have an argument. And so I want to separate that 2 plus 10x so it's not confusing. Okay, but here I don't have to do that because they're just factors. Okay, y equals 5 of x, 10, 3x. What do I do here?
Product rule.
Good, it's a product rule. So, who wants to do it? You guys want to try doing it? Somebody I haven't heard from. Who's there that I haven't heard from? Who wants to try doing this? Yes. Yes? Excellent. Perfect. Beautiful. Yeah, we're going to simplify here, no problem. Goes 15x secant squared of 3x plus 510. Okay. Determine the equation in standard form of the tangent to y equals tan of x minus 4 cos of x at the point where x is equal to 2 pi. So we know we're looking for an equation. We need two things. We need the slope. We need a point. So we can very easily find the slope by finding the first derivative. So let's start there. So what is the first derivative of tan of x? Let's start there. Derivative of tan x.
Secant squared x.
And then I have minus 4 times cos of x. So what is the derivative of cos? Derivative
Negative
of
sine.
x? Good, it's negative sine x. So here I'm going to have two negatives. And that's how I get my positive. Now, from here, we want to know the slope when x is equal to 2 pi. All right. So we know secant squared of x is the same as 1 over cos squared of x. Okay, so now what we're going to do is we're going to look at our graph, yes, to evaluate. So let's start with cos. When I draw cos, I know it starts at the maximum, goes down to the minimum, and then back up to the maximum again. And our period here is what? What's the period here?
2 pi.
Excellent. And so I can very clearly see here that cos of 2 pi is equal to 1. So I can sub that in. One squared, right? Because it's cos of 2 pi times cos of 2 pi. Now, sine of 2 pi. Well, sine is different. Sine starts at 0 and does this. And again, the period is 2 pi. So in this case, we see that sine is now equal to sine of 2 pi, which is equal to 0. And so my slope is just 1. So I have my slope. Now I need to find my point. So y equals, what's the expression? So they said at 2 pi, so tan of 2 pi minus 4 times cos of 2 pi. Okay. Tan. Tan of 2 pi. Who remembers what tan looks like? Who can tell me a little bit about tan?
It's like a cubic function, but multiple, and there's like an asymptote.
Love it. Is it an increasing function or a decreasing function?
Increasing.
Excellent. It's like a cubit that's increasing. Beautiful. And this just repeats, yes? Now, what is the period of tan?
Pi.
The period is pi. Excellent. So that means we've got pi over 2 this way and negative pi over 2. These are my asymptotes. Okay, these are my asymptotes. And maybe I'll label them like this. So if I were to keep going with this graph, if I were to keep going with this graph, so just copy, paste, where would my next asymptote be? So my first asymptote's at pi over 2. That's 90. Where would my next one be? Yes, I'm going to be
3 pi over 2.
Amazing. You're going to add pi. The period is pi. So you add pi to it, and you're right. The next asymptote is going to be at 3 pi over 2. So if my next asymptote is at 3 pi over 2, what is the tan of 2 pi? Think logically. It's 0. Good, excellent. It ends up being that part of your graph. I ran out of room here. But if I were to just copy and paste this graph, just like I will here, and I do it again in the next one, you will see that tan of 2 pi is equal. Okay, and now we've already figured out the cos of 2 pi. We know that it's 1. So I have my slope, I have my point, and now we sub into point slope. For sure you can. Absolutely. Yes, for sure you can. Okay, but it is beneficial to know your tan graph. Right? It is good to know what your tan graph is all about, but absolutely you can do it that way. Okay, so now y minus y1. So here I have y plus 4 equals, what was the slope? 1? X minus 2. And so I have y plus 4 equals x minus 2 pi. And we want it in standard form. And so it's going to be x minus y minus 2 pi times 4 equals 0. And it doesn't matter if you write minus 4 minus 2 pi or minus 2 pi minus 4. It doesn't matter. And now we have finished calculus. Now we have one more example. And you can call yourselves calculus captains. Do you like our calculus captain? He's an oldie. That's what a lot of my professors look like, actually.
Wait, so how many tests do we have left?
I'm sorry?
How many tests do we have left after the CPT?
So you have chapter 6, chapter 7, chapter 8, and then chapter 9 will be a CPT.
Okay.
Cool? All right, example 3. Find and describe the critical points for y equals 10 of x minus x, where we're given an interval. So where x is greater than pi over 2, but less than 3 pi over 2. Okay, so we're given an interval. What do I do? I got to find the critical points. Well, critical points we know means what?
First derivative.
Yeah, first derivative what? Equal to 0. Beautiful. Okay, so finding the first derivative of 10 of x minus 1 is secant squared x minus 1. Sorry, 10 of x minus x. It's secant squared x minus 1. You set it equal to 0. And so we want to find where secant squared of x equals 1. Well, secant squared of x is the same thing as? Yeah, so basically, if I cross multiply here, I want to know where cos squared of x is. Okay, so I don't want you guys to rely on your calculators. We're going to look at the graph. First of all, your calculator will only give you one result, won't it? But remember, there are 2 places where cos of x will be equal to 1, right? And actually many, there will be infinitely many places, right? Because this graph goes on forever and ever and ever. We want to look at it between pi over 2 and 3 pi over 2. So where do we equal? Where would cos squared of x equal 1? Now remember, it's cos squared of x, which means cos of x equals plus or minus 1. We're taking the square root, right? So between that interval, guys, is x equals 0 included?
One is pi, so there's anybody x equals 0 included.
So at x equals 0, we equal 1, but it's not included in, you got it. It's out of our interval. And at 2 pi here, it's out of our interval as well. So the only answer is pi. And not always, but most of the time, the interval that you guys are used to seeing is between 0 and 2 pi. Yeah?
If we look at like this,
Yeah.
we would have to write out like the 3 like solutions
Yeah.
there and then
Yeah,
say that, okay.
yeah, and say that they're inadmissible,
Okay.
right? Or just say like I did. It's up to you. You can either cross out the 2 and say inadmissible. Extraneous is another word that we use. Only x equals pi is an admissible solution. Okay? Okay, so that's our critical point. We've got to find out what about it now. I have a critical point. What do I want to find out about it?
If it's a max or min or
Good.
neither.
Excellent. You want to find out if it's a max or a min or neither. Okay? So I have the x value. Why don't we go ahead and find the y? We usually do it at this point. So it will be 10 of pi minus pi. So back to our tan graph. I like to review it. It's good to know. Tan of pi. What is tan of pi?
0.
Yeah, it's 0. And you know that because your period is 180. So this is pi over 2. This is negative pi over 2, this asymptote. And we know that this one is now 3 pi over 2. We add pi, that is the period. And so in the middle, we have our tan of pi. Yes.
We need to know like the tanx to get like and
No.
so yes, so the asymptote will always be the same.
Yeah, I shouldn't say that. You should know. If, would you be given a transformation? That's what it means. Most likely not.
Because like, what if the asymptotes are different?
If the asymptotes are different, you just have to shift everything, right? But most likely not. They're always going to be just can't. You're just solving, right?
So basically, it almost always be like zero.
Could be undefined.
Yeah, but most of the time it's zero.
Yeah, most of the time. I'll do it. Okay, so then therefore, you've got a critical point. At pi negative 5. We want to check if it's a max or a min, guys. Do you want to take a second derivative, or should we do a first derivative test in this case? You can do either. But in this case, we don't need to find the second derivative, so we might as well just do a first derivative test. All right, and I have secant squared of x minus 1. All right, so between pi over 2 and pi, is this function positive or negative? So how would you figure that out? Well, remember secant squared of x is 1 over cos squared of x. And so pick a value between pi over 2 and pi, plug it in, and see if it's positive or negative.
Negative?
Sure. Careful. What did you choose? What value did you choose?
Oh, sorry, I mean positive.
Positive. What value did you choose? Doesn't really matter, right? As long as it's between 90 and 180. You can choose any. Right? Okay, and now we need between 180 and 270. What do we get? Positive or negative? Anyone? Anyone?
Positive.
Yeah, it's positive. Okay, so what we see happening here is what? Max, min,
Either max or min.
neither. Excellent. It's neither. I don't have a change in slope. So it's neither. Good. Okay, so please notice, guys, in this first derivative test, I have my boundaries, pi over 2 and 3 pi over 2. And that's why I don't need to check outside of those two values. Yes, I don't need to check to the right of 3 pi over 2. I don't need to check to the left of pi over 2. Those are my boundaries. I only care about the graph in between those two values. Cool?
Wait, miss, if the interval was like 0 to 2 pi, would we have to do the asymptotes because it's tan?
You would?
Okay.
Yeah, remember, we always add our asymptotes in our derivative test. So yes, the answer is yes. Right? But you're saying that it's 10.
But in this case, the boundaries are the asymptotes, so we don't have to worry about it.
You don't have to worry about it.
Okay. Would we have to worry about that in the future?
No, to be honest, that's why these boundaries are given, right?
Okay, okay.
Yeah, to make life easier for you. But you guys know, when you're doing a first derivative test, you always have to consider asymptotes.
Okay, thanks.
Just to see this graph, that's what the graph would look like. 10 of x minus x.
Yes, so if we get a critical point that is not in our boundary, like in our boundary, it's outside of the boundary, then we don't use it in the in the interval, right?
Exactly. Exactly. Yeah, he said, well, just like here, you see how I got two critical values, two critical points that were not in my interval, then we just don't use them, right? We just say that they're extraneous, inadmissible. Yeah. Well, we write them.
But not down to the.
Exactly. Now, isn't that a pretty graph? Isn't that pretty? is 10 of x minus x. Cool. Are there any questions? Any questions? That's it, guys. That's your last calculus lesson. You've done it. Does it feel good?
Yes.
You say yes, yes. Thank you. And that's your homework for this lesson. Okay?
Miss,
Yes, tell me.
I have a question for I think 5.2 example 3.
Example 3 or the
Sorry, 5.4 example 3.
Like from my homework? Like from my lesson?
Yeah.
From my lesson. 5.4. Go to it.
5.4, miss, sorry.
Well, sorry.
Miss, can you switch it?
Oh, yes. You're talking about the attendance?
Yeah.
I did it, didn't I? I think I did it. I did it. Okay. 5.4, example 3. Example 3. So, yeah.
So like I just have a question about the form for a standard form at the bottom of the page.
Yes.
I think you mentioned this yesterday, but like I don't understand why we could just leave the a value as 2 root 3.
2 roots. Oh, here. I know, because it's not an integer, correct? Is that why you're saying that?
Yes.
You know what? I know. But by convention, it's used. In this case, it's used. You're right. It's not really proper standard form, is it? But in this convention, it's used. In this situation, it's used. I don't know, because it's true. I'm not sure. But in this case, it is used.
So like this is totally valid, right? Like we won't lose any marks then.
No, this is valid. In this case, it's valid. You're good.
Okay, and then Miss, I had an.
Yeah, go ahead.
Sorry, I was just gonna say I had another question. You can continue.
No, I was just going to say, so 2 root 3 is an exact value, and yes, you're right, it is, it's an irrational number, it's not an integer, but because it is still, we're not rounding, we're still able to show it as an exact value, we accept it in standard form.
Okay, thank you, Miss.
Yeah, no problem. Okay, what's your other question?
So like if we're writing like let's say a sort of similar equation, but in y equals mx plus b form.
Okay.
So like let's say we have y equals negative x minus root 3 over 2 plus pi over 4. Like would that be acceptable to just leave the answer like this, or should we like common denominator the the 3?
Oh, that's a good question. I would say it's better form to find a common denominator here and bring it together as one, since it is a y-intercept.
Okay, so we just have to find the common denominator between the b values, right?
Yeah, just the b value.
Okay,
Yeah.
thank you, Miss.
Because it's y equals mx plus b, so this very clearly states m, this very clearly states b. Now, to be honest with you, if you gave me this on a test, I don't think I would take off marks if you did not do this extra step, but this is better.
Okay.
Okay?
Okay, thank you, Miss.
Yeah, no problem.